All right, in section 13.4, we look at the definite integral. And we'll start off with some motivating exercises and look at sort of the main goal. The definite integral is going to be related to the area under the curve. When we say under the curve, we mean between the curve and the x-axis. So if you look at the picture on the right, you have the graph of y equals 0.25 x squared plus 1. That, of course, is a parabola. And I've only drawn it here from 0 to 6 or whatever. And I've shaded under that curve from the x values 1 to 5. And so that's what we're interested in finding, is what is the exact area under that curve between the x values of 1 and 5. All right, to help us do that, we'll need the following terms. First is partition. And a partition is a set of numbers between the endpoints of the interval. So we'll just say the closed interval a to b. So in the example, the interval is 1 to 5. All right, subinterval. That is an interval created by consecutive partition points. All right, so a partition is a set of numbers that are between a and b. They partition the interval a to b, and so we have these subintervals from a to b made up of the partition points from the partition. And basically, you're just going to divide up the interval into so many different pieces. The pieces don't have to be the same length, but when they are, that is called a regular partition. So a regular partition is a partition with evenly spaced partition points. Then we have a left sum and a right sum. A left sum is a sum created using left endpoints from subintervals. And of course, a right sum is a sum created using right endpoints from subintervals. I believe on your homework and in the book, they'll use notation that looks like this. L, and then it'll have a number, maybe a 4, and an R with a 4. So a left sum and a right sum with 4 partitions in the partition section. So just 4 evenly spaced. All right. So we're going to have to do several of these. And you'll have to sort of, you'll pick up on what's going on as we go through this. But we start off very coarse, let's say. we're gonna estimate this area. So our goal is to figure out what this area is. What is that area? That is the goal today. And we have several examples leading us to that. So the first one is to estimate the area under the curve between 1 and 5 by using partitions of intervals with 2 equal subintervals. So we're going to go from 1 to 5, and I need to split that up into 2 subintervals. So it needs to be 1 to some number, and then that number over to 5. If you have 2 subintervals, you only add 1 extra point. And we want these to be equal, giving me a regular partition. What number between 1 and 5 would make the subintervals the same size? 3. All right. So we're going to go from 1 to 3 and 3 to 5. So your partition is big P, and we're going to write that as a set, 1, 3, and 5. The intervals will be the interval from 1 to 3 and the interval from 3 to 5. And technically these are subintervals, right? Subintervals. We want to use a right sum. And so basically what we're going to do is we're going to form a rectangle that covers the curve as best we can based on the endpoints from my partition. So if we want a right sum, that means we use the right endpoint. I'm going to project up from x equals 3 up to the function, like so. And then I'm going to create the rectangle that has this new point that we just drew to as the upper right vertex. Oh, close. All right. So we've covered up the entire function with that rectangle. Now this is overkill, right? I'm trying to cover the curve to find the area under the curve, but we only have 2 partitions, so we don't have much choice here. So we covered up the whole thing there. Maybe you want me to do a different color on that? Let me try a different color. Let me try. You want to see the outline? No. Let me try this. Let me try this. I'll show you what I normally do before I had the tablet. I would just do this. Well, no, I'm not doing that anymore. Don't do that. Do regular. There we go. We just draw it like that, and we just do this. You like that better? Okay. What we need is like translucence. All right. And then what would I do for the other one? I go up from the right side of this interval, subinterval, from 3 to 5, go up along the 5, go to the curve, go back over to where it's x equals 3, and then come back down. And now we have this shading. So, now, as bad as it is, the total area that we have here is the estimate for the area under the curve. So we need to figure out what the total area is. That's where the rest of the chart comes in. Delta x is the length of the subinterval. What is the subinterval length? 2 and 2. And then we need to compute f of what I call xi star. It's very creative on my part. The computer uses a ci. So ci is the same as my xi star. Now, xi star is the x value that we have chosen to represent the subinterval. We are doing a right sum, so in this problem, it is the right endpoint. F of that point is the function value at that point, which is the height of the rectangle. So on the first subinterval from 1 to 3, xi star is 3, and f of 3 is, and then we figure this up, we can use our calculator on this, that would be 3.25, plugging that into the function. And then what does that tell me? I have a base and I have a height. Base times height is the area of that rectangle. So that would be 6.5. On the second subinterval, xi star is the right endpoint again. That's a 5. We go up to the function value. The function value is 7.25. Multiply to get the area of this rectangle. That would be 14.5. So the total covered is 21. So our first estimate for the area under the curve is 21. Is this an overestimate or an underestimate? Overestimate. Because you covered the whole thing. So recapping. You create a partition based on the number of intervals you need. If it's regular, it has equal subintervals. If you use a right sum, then you create rectangles based on the right endpoint of each subinterval. Compute that area. So it's delta x is the distance across, f of x is the height, base times height is area. Add them all up, and voila, that's your estimate. Yes?
What did you plug into the right side?
For the first one, I plugged in 3. And for the second one, I plugged in 5. Now, why did I choose 3 and 5? Which ones?
On the right.
Right endpoints. Yeah. Yeah. Because there'll be some problems that say use the left endpoint, a left sum. There will be some problems that say use the midpoint of the subinterval. So you have to find, like the midpoint of these would be 2 and 4. So you could do that. There will be some that have weightings on, like you're going to use the point that's 1/3 the way from the left endpoint instead of and 2/3 away from the right one. So you can use any point here you want. They're just different things. This is a right sum. We'll do a left sum. There could be a midpoint sum. You could even use just points I give you. We'll do that one as well. So all sorts of stuff. All right, let's look at the next page, next example. And on our next example, we'll do the same thing. It's the same function and everything. But we're going to work our way up to 4 equal subintervals. So if I need to divide the interval from 1 to 5 into 4 equal subintervals, what is the partition? So it starts with 1 and it has to end with a 5. So what numbers do we use in the middle if we want 4 equal subintervals? Yeah, it's just 1, 2, 3, 4, and 5. So write that down as your intervals. 1 to 2, 2 to 3, 3 to 4, and 4 to 5. What is delta x for each of these subintervals? 1. Draw the rectangles based on the right endpoint. So we'll go over to where f is 2, go up to the function, then go back across, go over to 3, go up, go over to 4, go up, and then go over to 5. Oops, give it. And shade that in. Now, you can use your calculator to give you these values that you'll need for your chart. If you go to y equals and plug in the formula, it's 0.25 x squared plus 1. These are regular partitions, which means the endpoints, the parts in the partition come off regularly. So you can do table set. Tables, for this example, table start should be 1, and then delta table is the same thing as delta x. So this is going up by 1s. Independent should be auto. And then second table, and then that will give you the numbers. Now be careful. Remember that you're using a right sum. So the numbers start at 2. So f of 2 is 2. F of 3 is 3.25. 4 is 5. And then f of 5 is 7.25. Would you like me to show you this on the overhead? Okay. So I've entered the function as y1. I've gone to second table set, which is the shift of the window button. And we're starting at 1, and my partition points go up by 1. Independent is set to auto so that it will automatically fill the table. And then second table gives me the table values. We're using a right sum, so the first number we use is 2. And then 3, and then 4, and then 5. All right. Now, we're still finding the area. What is the base of each of these? 1. That's delta x. All right, so delta x is the base. F of xi star is the height. And you know that the area of a rectangle is base times height. These are multiplied by 1, so they're all just these values here. And if you add them together, you end up with 17.5. That is our new estimate for the area. Is this an underestimate or an overestimate? Okay. Overestimate. Is this a better estimate or worse estimate than the one in the previous example? It's better, and how do you know? Yeah. In the first one, the first rectangle included this area, which is, can y'all see that? It doesn't look like it. It included this area, which is clearly not under the curve. It also included this piece right here. What we have done in this step is called a refinement. We took a partition and then we refined it into more points. More points give you better answers. Okay? And so that's the game. You keep making refinements until you get this as close as you want it to be. And so we keep working at that. So the next one, I'm going to turn you loose with your partners here, is to do the same thing but with 8 subintervals. Now, yeah. So go ahead and do example 3. And it's a regular partition with 8 subintervals. Now, you also might want to be thinking about how to compute delta x given any number of subintervals that there's a point. See if you can figure it out. All right, so draw the rectangle. Okay, that's very nice. Very nice. The shading. It looks like those 1950s maps of New York. Shading. Shadow. I'll do that. I'll clean the class. Would you like to see another shortcut while we're on the topic here? Have you figured out what delta x is? 0.5. All right. So if you go down to y2, we can tell it to do 0.5 times the height function. That would be 0.5 times, and then we can call up y1. Y1 is the height function. So vars, right? Did we do this already? Vars, y vars, function vars, y1 of x. And that says take 0.5 of the y1 value at that point x. So there's 0.5 times each of those. And you just got to remember to change it based on whatever delta x is. Calling a function, just like you call it that function. So you have to say y1 of x. So it's y1 and it's like f of x. How we direct that to that? All right, so you should have got the partition 1, 1.5, 2, 2.5, all the way up to 5. There are 8 of them. Delta x is 0.5 for every one of them. It's a regular partition. And then f of, and the first number we use, because we're doing a right sum, is 1.5. So f of 1.5 is 1.5625. And you multiply that by 0.5 to get the area. So it's 0.781, let's say. And then f of 2 would be 2. And so that's the area of 1. F of 2.5 is 2.5625. Area 1.2813. And then I'll just fill these in. Are these the same numbers you're getting? I hope so. And 1.625, 2.0313, 2.5, 3.0313, 3.625. And for grand total, I've rounded it here. It's 15.88. Your rectangles look like this. Oops, that's not right. Something like that. All right. Overestimate or underestimate? Over or under? Over. Yeah, still over, but we're still knocking some up. And again, I think the book would call this R8. So check into that. It should be R8. Incidentally, has anyone come up with a formula for delta x? B minus A. And then what? And then what? So in this case, delta x was 0.5. B minus A would just be 4, not 0.5. But you're on the right track. There is a B minus A in this. And you divide by n. So B minus A represents the length of the entire interval. You're going to divide it into n parts. 8 parts. All right, example 4. Estimate the area under the curve. This time, using a left sum. So we would use pretty much the same information as before. It's the same partition. So it goes from 1 to 1.5, 1.5 to 2, etc. Delta x is still 0.5. But the rectangles have changed. It's now a left rectangle, left sum. So you would go up on the left side of the rectangle and then go across. So we're going to start at 1 and go up and over like that. Then start at 1.5 and go up to that height, and then go over and down. And then the last one is quite deficient. Will this be an overestimate or underestimate? This should definitely be an underestimate. And I'll go ahead and fill in these numbers. The first one is different, right? Because you're using the left sum. So f of 1 is 1.25. The rest of these numbers are all the same. They're just moved down the table a little bit. And you can get these from your calculator. It's the same table screen that we just saw. And multiply these out. I'm doing some rounding here. And that adds up to 12.88. That would be L8. Which part?
How do you get at the Y? Like just on the how to get that second set of numbers to multiply times 0.5.
The function? Did you do the table set? Yeah, the table starts at 1 or 2 or whatever. 1, and it goes up by 0.5s. All right. That fix it? That fixed it, right?
Yeah. Do you always look at the Y one?
Well, it's whatever you have set up here. The y1 is the function value, so that's f of xi star. y2 is the product. It's the base times the height, so that's the area. All right. In example 5, the partition is given to you explicitly. The partition is 1, 2, 2.5, 3, 3.8, and 5. Complete the table and shade the graph. Use the points listed in the chart for xi star. It's not necessarily a left or right endpoint. And then determine if we have an overestimate or an underestimate. So the partition goes from 1 to 2, 2 to 2.5. Oops. .5 to 3, 3 to 3.8, and 3.8 to 5. This is not a regular partition. So the delta x will change for each interval possibly. So what is delta x for the first interval? 1, second, 0.5, 0.5, 0.8, and then 1.2. Let's draw the rectangles. Now, the rectangles are based on the height of the graph at each of the individual xi stars. So the first xi star for the first interval goes for interval 1 to 2, starts at 1 and goes on up. Now that covers the subinterval is from 1 to 2, so it goes all the way over to 2. So when you have a irregular partition, you're going to have different lengths going across as well. The next subinterval goes from 2 to 2.5, but its height is based on the height at x equals 2.25. So that's the middle of this. So we're going to go up in the middle, and it's going to be here as the height. So it's not a left or a right rectangle. Same thing for the next one, 2.5 to 3, but the height is based on the middle of that, 2.75. So we go up in the middle. Let me get that there. The next interval goes from 3 to 3.8. That is going to go almost all the way to 4 there. The height is based on 3.5. So we're going to go up 3.5. And then go over towards 3.8 and then come down like that. You see how this is just all over the place? The last one goes from 3.8 over to 5, and the height is based on when x is equal to 4. So it's going to go up to that point there, going to go back a little bit, and then all the way over to 5. Now you can use your calculator to compute these values for you by changing table set from auto to ask. The document camera. So the first xi star value is 1. So that tells me the f of xi star is 1.25. Now we can't use y2. You can't use y2. y2 is based on it always being 0.5 times the height. So we can't use that. In fact, you can turn that off if you want to. Ding. Do y'all know how to turn off an equation? Go to the equal sign and de-highlight. Is that a word? So you press enter and it highlights it. You press enter and it unhighlights it. So that turns it off. But you might want it later. Okay. And then 2.25. So the f value would be 2.27. And then the next xi star is 2.75. That's 2.89. 3.5 is 4.06. And then 4 is 5. Now take each of those f of xi star values and multiply them by the rectangle length or base. So it's delta x times f of xi star. First one is 1.25. The next one will be 1.13. And then 1.45. And then 3.25. And then 6. 13.08.
What's the symbol called with the x?
Delta?
Not with the star and this star.
Xi star?
Exactly.
Yes, it's a star. Over or under? That can't be both. It's hard to tell, isn't it? Yeah. Because you got a little bit of over here. Oh, that's a good bit over. But you're missing this piece, and you're missing all of this. But maybe all of this and this sort of counterbalance each other. It's hard to tell. How did we know that the other ones were clearly over and under estimates? Yeah. So what was so special about x 0.25 x squared plus 1 going from left to right? Increasing. Yeah, it was increasing. So if a function is increasing, then all of its right rectangles will consume it and then some, but all of its left rectangles will be under it. This one we don't know. We don't know enough yet to figure that out. And we will, and the only way to know is to actually figure it out. So this one is a mystery. Okay. So that's the premise. And the main idea is to keep going. Take another refinement, and keep going. And what should happen is, as you take more and more refinements, necessarily the width of your rectangles have to get smaller and smaller and smaller. You have to pick numbers inside the rectangles to find the height. So as the rectangle's widths get smaller, the choices that you have for picking the heights are limited, which then forces those rectangles to pretty much be exactly the curve itself. So you don't get this piece over that. Right? I mean, you will as long as n is finite. But then, this is calculus, so what do? We take a limit. Take the limit as the number of partition points goes to infinity, and then the rectangles all line up on the curve itself, giving you the exact area. Okay. And so that idea is related to what we call the Riemann sums. And the Riemann sums are still finite stuff. So Riemann sums. So given a function f, an interval a to b, and partition P that is equal to A, which is also called x sub 0, and then x1, x2, x3, dot, 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 all the way over to B, the right endpoint, which is also called x sub n, S is equal to the sum of f of xi star times delta xi for some point x sub I star in the subinterval x of I minus 1, x sub I. And delta xi is equal to xi minus xi sub x sub I minus 1. So that's what you were computing earlier, is the Riemann sums. This piece right here is the formula for area. It is the base of the rectangle over a small subinterval times the height of that rectangle over that subinterval. The xi star is in the subinterval, and it can be any point, some point. Could be the left endpoint, could be the right endpoint, could be the midpoint, could be the 2/3 point, it doesn't matter. It could be random, like the one we just did. Here we've opened this up. This is delta xi. I have to put an index on this because there's no guarantee that the partition is regular. So the delta xi is just the length of the subinterval. It's the right endpoint minus the left endpoint of the subintervals. That's all it is. And then what do you do with the areas? You add them up. You add up all the areas, and that gives you the Riemann sum. Right. So this is sort of the math jargon for what you were doing, and doing it sort of in general. And now we get to the definite integral. So let f be a continuous function on a to b. If you take the limit of the Riemann sums for f on the interval a to b, this is called the definite integral, and it is denoted by the following. I is equal to the integral from a to b of f of x dx. So the symbol looks very much like an indefinite integral that we did yesterday, but it's now a definite integral. And what you do is you tack on the endpoints of the overall interval from a to b. Please note that when we go from a to b, the a is on the bottom and the b is on the top. We still have the integrand f. A is called the lower limit of integration. B is called the upper limit of integration. All right, now the geometric interpretation. So the integral from a to b of f of x dx, it's very much related to area, but it is signed area. So it is the sum of the signed areas between the graph of f and x-axis on a to b. Again, the a to b are the limits of integration. All right. This is where you have to get this straight in your mind geometrically. If I just give you a shape and say find the area, that is always positive. If you find the integral over some distance, that could be positive or negative depending on various things. Number one is direction that you're integrating. If you integrate from left to right with things above the x-axis, that's fine, that's positive. But if you reverse the integration and go from right to left, that could be negative. The other part is if you are below the x-axis and still going from left to right, that's negative because you are below where the y values are negative. So you're basically accumulating, quote unquote, negative area. All right. So here's an example that explains all this. Example 6. The actual areas of these regions are shown. So the actual area here is A, the actual area is B, and the actual area is C. If these were just geometric things someplace else. Now, when we take integration and integrate these regions, well, then we could get some other things. So let me show you. Question 1 says, what is the integral from -3 to -1? So -3 to -1 would be the area under the curve, between the curve and the x-axis. That area is above the x-axis, so that's okay, and that's A. Whatever A is, 4, 6, whatever. Now, question 2. What is the integral from -1 to 5? So x equals -1 starts here. It goes over to x equals 5. So we're going to take the combined area, but we've got to use their signs. In this first part, going from -1 to 2, the area of that curve is B, but it is below the x-axis. So the integral is -b. Then continuing on from 2 to 5, the area is C, and that is above the x-axis, and that is positive C. So the integral from -1 to 5 of f of x dx is -b plus C. All right, go ahead and try these with your partner. Do the rest of them. Okay, so the integral from -1 to 2 is from -1 to 2, that's B, that's below the x-axis, so that's -b. The integral from -3 to 2, A is above, but B is below, so that's A minus B. And then from -3 to 5, well, you're going to get it all, A, and then down below for B, plus C. So question over signed areas.
So it's just negative or positive depending on where the side is.
And which way you're integrating. If you're integrating from left to right, then you don't have to think about that at all. But we'll get to these properties here as well.
What if you're going backwards? So if you're
Yeah.
going like 2 to -1.
Yeah.
So but the B's below, so with that, with the negatives cancel out.
Yeah, that's rule 2 here, what we have here. So if you go from A to B, then that is the opposite of going from B to A. So suppose you were going to integrate from -2 to 1, then that's okay, right? That's some number. But that would be the opposite of going from 1 to -2. Right? Yeah. So and then whatever happens otherwise, right? So you could be going from right to left of a function above the x-axis. That would be a negative area because you're going backwards. But you could be going from right to left of something below the x-axis. That's then positive again, because you went backwards and it was below there. So yeah, so that's what you have with property 2. Property 1 says if you go from A to A, then that integral is 0. Property 3 says if you go from A to B of k times the function f of x, then you can pull that k out in front and then just take the rest of the integral. K is a scalar, so you're sort of taking out the scalar and saying I'll handle it later. 4 is if you have two functions that are added and you're taking their integral, then you can split that up and take the integral of each individual function and then add the results. Same thing for subtraction. And then 5 says if you're going to take the integral from A to B, that is the same thing as taking the integral from A to C and adding it to the integral from C to B. So in other words, if you had some sort of situation like this, here's A, here's B, right? Okay, like this. Then this entire area can be broken into two pieces. And so you have area 1 and area 2. And then the sum of those two areas is the area of the whole thing. Like so. That's the easiest way to explain that. You can pick any point to split this up. Okay. What's interesting is the C point that we picked to split it up doesn't have to be between A and B. You could pick C out here, and this result still works. That's mind-blowing, isn't it?
Would that be used mostly for calculating areas that are like kind of like the last negative for something above and something below? Like for example, last is -3 to +2 that goes with A and B.
Yeah, you can use it for that.
See it like -1 with A.
The techniques we'll use tomorrow will take care of that for us, but in general, yeah, you can do that. All right, let's look at example 7. You are given these answers. Now, tomorrow we learn how to actually find these answers. Today, I just give them to you. So assume that these are true. And then we want to compute the following items. How many of them are there? There are 5 of them. Okay, I'll do one, and then I'll let you do some. All right, so the first one is, what is the integral? Whoops, what happened? What is the integral from 0 to 2 of x squared plus x dx? We need to split that up. Which rule will split up x squared plus x? Rule 4. So we're going to get the integral from 0 to 2 of x squared dx plus, oh, and by the way, do you know what the dx, where the dx comes from now? I should have mentioned this earlier. That's delta x. Oh. Yeah, from the Riemann sum. Yeah. All right. And then plus the integral from 0 to 2 of x dx. All right, what is the integral from 0 to 2 of x squared? And what's the integral from 0 to 2 of x? 2. So that's 14 thirds. All right, go ahead, work with your partner. Do some manipulating to the given intervals to change them into things that you know from the top 3 there. And go ahead and finish the other 4 of those. That's it. Oh, you can't take 2x. You can't take out the variable integration.
Second draft.
I don't know about third one. We have to check. Mm-hmm. All right, let's check them. So number 2, we have the integral from 2 to 0 of x squared. We don't know that one, but we know from 0 to 2. So I need to flip the limits around, and I need to go from 0 to 2 of x squared dx. Now when I do that, what do I do to the value of the integral? We negate it. Right? So you can flip the limits as long as you negate the integral. So that would be negative 8/3. All right, part 3. We have the integral from 0 to 2 of 6x squared minus 2x. So first thing I need to do is split up the integral into 2 separate integrals. Now, we don't know the integral of 6x squared, but 6 is a constant multiple, and I can factor that out. So this becomes 6 times the integral from 0 to 2 of x squared dx. Same thing with the 2. That factors out and becomes 2 times the integral from 0 to 2 of x dx. And then we know these. This is 6 times 8/3 minus 2 times 2, which is 12. Questions over number 3. So we used rule 4 to split it up. Then we used rule 3 to factor out the constant multiples, and then we evaluated. Number 4 is 0 by rule 1. The integral from a number to itself is 0. And number 5, the integral from 0 to 3 of 3x squared. So the first thing I can do is factor out the 3. And this becomes the integral, 3 times the integral from 0 to 3 of x squared dx. Now, on your chart above there, the information given, you don't have the integral from 0 to 3. But what do you have? You have 0 to 2, and you have 2 to 3. So this is rule 5, where you can split it up anywhere. I choose to split it up at 2. So the integral from 0 to 3 is the same as the integral from 0 to 2 plus the integral from 2 to 3. And we'll just fill in the rest of this with the same function here. And those are things that I know about. So 0 to 2, the integral of x squared from 0 to 2 is 8/3. The integral from 2 to 3 of x squared is 19/3. Distribute the 3 and cancel the denominators, and you get 8 plus 19, which is 27.